Hello everyone, welcome to lecture 23 of Mathematical Modeling and Simulation. In this lecture we are going to understand about Monte Carlo simulation. In last lecture we talked about pseudo random number generation, and even in the previous two lectures we have discussed in detail what is the meaning of pseudo random number and how to generate these pseudo random numbers. So now we need to answer the question why we were learning the techniques of generating these pseudo random numbers. So the answer is because we need them to perform simulations of certain systems. So because the randomness is related with probability, so as I've already explained to you, these kind of systems, or you can say the models, are working for stochastic processes which involve some sort of uncertainty in them. It does not work for deterministic system. So we employ the random number generation in performing simulation of various stochastic processes, and specifically today we'll be learning about one such simulation, which is Monte Carlo simulation, so which involves random sampling and has many applications. So we'll talk about this in detail. So firstly we are going to talk about in general what is simulation, what's a brief history about it, and then specifically we'll talk about Monte Carlo simulation and examples. So as such, there is no formal or precise definition, but still we have the some statements in order to understand the meaning of the word simulation. So firstly, I'll suggest you to just pause the video and think about the word simulation whatever comes to your mind. So you can all have the very basic example of that when we go to learn to drive a car or any other vehicle, so the driving school just don't directly hand over you the vehicle to drive, but firstly they'll let you try your hands on the simulator. So a simulator looks like something real. So the simulation or the simulator there particularly looks like as if you are driving on a real road, but you are not driving on a real road. So you can say it's like a visualization or an animation or an exact replication of the real process, but it's never going to be exactly equal to the real thing. So simulation is similar to model, but it has a interface where we can visually see the things happening over time or space. So it's dynamic in its nature. So simulation of a system is the operation of a model in terms of time or space. So the model is operating, it's working, like it's something like you're running an algorithm. After say 5 seconds, you get an answer to your problem. But if you want to live look at all those calculations happening, so that's like operation of the code you want to experience with every and each and every calculation, each and every second of it. Then if you see that, if you're able to visualize that, so that means you're looking at the simulation of it, how the code is simulating. So that's the general meaning of simulation, that it is the operation of a process or a model in terms of time and space, and it helps to analyze the performance of an existing or a proposed system. So suppose you have developed a new software, so you will first show its demonstration through simulation, how it's going to work without actually testing it on the real machine or whatever field it belongs to. You'll first try it on a simulation. You first run its simulation so that you can judge the or look at the performance of the system. And we have another definition by Shannon. It says it's a process of designing a model of a real system and conducting experiments with this model for the purpose either of understanding the behavior of the system or of evaluating various strategies. So that's essentially the same thing which I've just explained to you. It's a imitation of the real system. So here is an interesting quote by Elon Musk. It says, "We all are probably living in simulations." So if you have time, just Google this and you'll find the interview in which he shared this thought. He did not say exactly these words, but more or less the statement meant this only. So it's a very interesting conversation. Anyway, so that's just to give you a different viewpoint of simulation, but let's go back to the content, and now we'll talk about a brief history about it. So in 1940, a method named Monte Carlo was developed by researchers John von Neumann, S. Ulam. It's Ulam, U-L-A-M. Edward Taylor, Herman Kahn, and physicists working on a Manhattan project to study neutron scattering. So first time then they coined the word Monte Carlo simulation. So some experiment was being performed by these researchers. So they came up with this word. In 1960, the first special purpose simulation languages were developed, such as SimScript at the RAND Corporation. So this RAND is basically running for the random. The short form is RAND. You will see, you might be already familiar with this command if you use there, but basically it's just another era of simulation languages started with this. In 1970, mathematical foundations of simulation were much strong. In 1980, PC-based simulation software. So it's something like gaming, you can see. The games which you are playing on your systems, computers, they are all PC-based simulations. Graphical user interface. So these are the things I'm talking right now, just on the previous slide, that where you have a visualization of the things happening. So there's a graphical user interface involved, and object-oriented programming were developed. So the visualization or animation kind of view of the simulation was developed in this time, and then later on it became more advanced. Web-based simulation, animated graphics, simulation based optimization. So animated graphics, you can say the animated movies which you watch is also one kind of a simulation. Markov chain Monte Carlo method. So this is also a very famous, well-known methods. MC, Markov chain Monte Carlo method. So Monte Carlo method is a general technique, and particularly when this is applied to Markov chains, then these are known as Markov chain Monte Carlo methods. We'll study about this Markov chain when we'll be studying the stochastic models in this course. But this was just to give you an overview of that how the simulation has advanced over these years. Now we are specifically talking about Monte Carlo simulation. So here's few remarks about it. It's a technique used to understand the impact of risk and uncertainty in financial, project management, cost and other forecasting models. So that's just a statement given by the person who is working in, say, financial mathematics or studying of economics and finance. So from his point of view, Monte Carlo simulation is a technique used to understand the impact of risk and uncertainty. I begin my lecture with this statement that stochastic processes are those processes where certain kind of uncertainty is involved, while in deterministic process we do not have uncertainty. We do not have any risk. We have a fixed output. We have a fixed input and a fixed output in the deterministic ones. So, but in stochastic ones, we have a risk involved and uncertainty involved. So there, to estimate the risk or to predict the outcome of our experiment is going to be executed through Monte Carlo simulation. A Monte Carlo simulator helps one visualize most or all the potential outcomes regarding the risk of a decision, that if you choose this, then this might happen. If you choose this, then this might happen. See, the answer of a stochastic process is never that this is going to happen. It's always a word, this might happen or this probably would happen, right? So that's why I'm speaking in that context. Apart from these, it has many applications in understanding complex dynamical systems, and they form an important part of statistical mechanics. So right now, all things we are talking about in terms of finance and cost, but we should not forget they have many other applications. Also, they have the applications in supply chain management. They have applications in physics. In physics these days, whatever the macroscopic models discussed, wherever statistics is applied, you have statistical physics, also known as statistical mechanics. So there, all the simulation models are the Monte Carlo simulation models because of the involvement of probabilities or the randomness into the systems. So that's a general overview of Monte Carlo simulation. So this technique is named after Monte Carlo Casino in gambling capital city of Monaco in Europe. So this should come to our mind that why this particular name has been given. Monte Carlo simulation, why it's just not called anything else, why there is a specific word Monte Carlo attached with it, because Monte Carlo is a famous casino in the city of Monaco. It's actually a country, it's a very small country close to the France, and this country is famous for its gambling. You can say all the world famous casinos are present over there, and Monte Carlo is a very small area in that city of Monaco. So that's why, because the gambling and all these things are random. So because of the connection between these two things, the simulation which we run to understand the randomness and the uncertainties, so that's why that randomness or the uncertainty is making a connection there. That's why the simulation is called a Monte Carlo simulation. So there's an interesting example. The house always wins. There's a famous song on this also. There's a story on this also. So what does this mean? You can understand it by reading this. So you consider a game, an imaginary game in which our players, say we have a player X, rolls and imaginary dice to get an outcome of 1 to 100. Say there's a dice which can give an outcome of 1 to 100. So if X rolls anything from 1 to 51, the house wins. But if the number rolled is from 50 to 100, X wins. So it's like dividing the outcome space. So you have your sample space. So your sample space is like 1 to 100. Any number can come as a output, right? Your output is going to be out of these 100 numbers. So there's a decision made now that if the number comes between 1 to 51, then the house wins. But if the number rolled is from 52 to 100, then X wins. So now we want to know what is the chance of X winning. What is the probability, or what is the, you can say, we just want to make some quantification that uh, is there any parameter to know whether X is going to win or not. So let's suppose X bets $1 on this game, then you can calculate the probability of X winning is 49 by 100, because you see out of these 100 numbers, X is winning in this situation 52 to 100. 52 to 100. So how many numbers are these? These are 49. So the chance of winning, the probability, the number of favorable cases for X is 49 by and the total number of cases are 100. So you know the basic definition of probability of an event is the number of favorable outcomes divided by the total number of outcomes. So it's 49 by 100 is the probability of X winning, and obviously the probability of the casino winning is 51 by 100, because there they have the numbers from 1 to 51. And expected profit, if you want to compute for the player X, it will be, you can see, because he's betting $1, so it's 1 into 49 by 100 minus 1 into, because $1 means if he wins he gains $1, if he loses then he lose $1. So that's why it's 1 and 1 is multiplied. So this turns out to be minus 2%. So expected profit, this is the same thing we study in game theory also, when we compute expected payoff of a particular player when there are only two players. So basically we are doing the same thing, we are computing the probabilities, and then the exact profit we cannot compute, it has to be the mean of the probabilities have to be multiplied with the profit. So the profit is $1, but the probability of getting this $1 is 49 by 100, and the probability of losing this $1 is 51 by 100. That's why it's multiplied with probability, and that's why it's expected profit. And it's turning out to be negative, you can see. So negative profit means a loss. So that's why the house is always going to win. Right? So that's the meaning of the house always win, because whenever you are computing the expected profit for the player, it's always negative. So we know that from game theory, when we have a two-person zero-sum game, Zero sum game means whatever the one person wins, the other person loses the same amount. So if player X is losing 2%, so that means house is gaining 2%. So X is always losing and the house is always winning. So that's why the casinos are earning money, you can see. Because even if very few people just win by chance, but the probability of winning decreases as you play more and more, right? Because these expected profits, which are written over here, this is not like that X will just play the bet for one time or two times. He has to have, to get this profit, 2%, we have to have simulation trials of say 50, 100 or 1000 trials. After that, we'll come to know that the results are matching with this. So this part we'll learn in the next example, that if we want to have an accurate prediction of Monte Carlo simulation, we want to run the simulation for a more number of times. Here, this example, I was not showing you how to run the Monte Carlo simulation, but this is connected with that. This idea in which we computed the probabilities, this is the fundamental of Monte Carlo simulation. So that's an interesting example to understand the meaning of this probabilities and computation of expected profits. And given a chance, you can simulate it. You can actually get to know the output is turning out to be negative 2% if you simulate this model. This is a theoretical calculation done, but you can get the same answer through Monte Carlo simulation. So anyways, we will do that later. Right now we are going to talk about another example, which is the very first example which you should know if you want to learn how to do Monte Carlo simulation. So now I'm telling you the how part. I have told you what part, why it is required. See why it is required, because it has many applications. What it is, we have just seen the definitions and all. So this is an important question now. How to perform Monte Carlo simulations, and for that I have picked a very simple example, coin tossing. Because whenever we study the topic stochastic process, you say, so stochastic process has the simplest example is coin tossing, because a process whose outcome is unpredictable, we call it a stochastic process. So coin tossing is an example of a process whose outcome is unpredictable. We do not know whether the head will come or the tail will come. Although the sample space is finite, we know that there are only two possibilities, but still nobody knows what exactly is going to turn up, the head or the tail. So that's an example of stochastic process. So now we'll learn how to perform the Monte Carlo simulation of coin tossing, and with this you will see that this is the benefit of doing it on computer or doing it in lab through a software or language, you can say. We will not be using any actual coin, but still will be tossing it like say 10 raised to power 9 times. So let the computer toss the coin. So that's the another way of looking at these simulation. These Monte Carlo simulation come under the category of computer simulation. So computer simulation is a very advanced, and you can say it is the most uh, important and interesting things going on these days, because computer simulations are better than all other kind of experiments and simulations, because they do not require anything. They just need to be virtually imaginary. You just have to create imaginary objects and run it through the computer code. So there is no risk to anybody. For example, I'll just give you an example. You want to conduct a simulation of a road, say you launched a new vehicle or a drive test you want to create on a road. So you need a road to test, right? A real road. So resources are required there. But if you want to do the same thing virtually on a computer, so you just need a computer. So even if your experiment fails, nobody is going to die in a computer, right? Because it's virtual. So that's the meaning of, that's a benefit of computer simulations. So same thing we are going to do here. In stochastic process, we are going to perform the example of a Monte Carlo simulation using coin tossing example. So let's do that. Okay, so it's simply, you have to mathematically quantify your outcomes. For example, let me just change this. if I take a head is 1 and a tail as, you can say, 0. So there are only two states possible, or this is also not required, or you just talk in terms of the probabilities. That suppose this is an interval 0 to 1, then we know that the probability of a head coming up is half and the probability of a tail coming up is half. So your interval is divided into exactly two halves. So what we do is, this is now beginning of the steps of simulation. So first we generate a random number. So this is what I was talking about. In the previous two lectures, we have learned already how to generate random numbers, the pseudo-random numbers using computer algorithms. So whatever algorithm we use, but we generate a random number lying in the interval 0 to 1, right? And then second step is, say you call this number R. If that number is less than 0.5, then we call it a head, and otherwise if that number is greater than equals to 0.5, we call it a tail. It's okay, you can call this a tail and this a head, that's okay, because both are equally likely. So it's just we have to associate the number with the outcome. The outcome is a head, so you have to associate it with some mathematical number. So we have associated that with the random number, that if r less than 0.5, we will, it will give the interpretation that okay, head has appeared. If the random number is greater than equals to 0.5, it will give the interpretation that tail has appeared. And now we will do this step number 2, say some number of times. So because these are stochastic processes, the runs of the experiment or the simulation has to be large as possible. Because see, if you will be just performing 2 times it, say you just perform the experiment 2 times, say both of times head comes, so you will assume that the probability of head coming is 2 by 2, because 2 times head comes and 2 is the total number of trials which you performed is 1. But this is the wrong answer, because we know that probability of head coming is half. Then suppose you run the experiment 10 times. Then suppose 8 times head comes and 3 times tails come. Then you will conclude that probability of head is 8 by 10 while probability of tail is 3 by 10. So which is also incorrect. So you will see this in lab, we will do this experiment, and there you will see, as we will increase the number of our trials of experiment or simulation, we'll start getting these probabilities equal to 0.5, very close to 0.5. So from there we will conclude that okay, whenever we have to run the Monte Carlo simulations for any system, the number of trials, the number of simulation runs has to be large, and then only we take the averages. Okay, so that's the basic idea of how to perform Monte Carlo simulations. And then you count how many times head comes, how many times tail comes, and divide that. You know how to compute the probability. This just I have shown you the number. If the probability of head you are computing, so the number of heads by the total number of runs of simulation, and similarly the probability of tail will be the number of tails divided by the total number of runs of the simulation. So basically here we have taken it for a simple example, at least because we know the answer already, so we can match that our simulation is giving us the correct answer. So I hope that example is clear. Now we are going to take an example of Monte Carlo simulation to compute the value of pi. This is a very interesting example. So this is not specifically related with this course, because I told you that applications are different. But this is just, we need to know that how basically the Monte Carlo simulation works. This is a very famous example. You want to compute the value of pi using Monte Carlo simulation. So let's do that. So you draw a circle. You enclose that circle in a square, and suppose the radius of the circle is 2r, radius is r, so the diameter is say 2r. Then we know that area of the circle is pi r square, Area of the square will be 4r square because the side of square will be 2r, because the way you have made this diagram is helping you decide that side of the square is 2r, so that makes area of the square is 4r square. So if you divide these two areas, area of square and area of circle, so if you divide area of circle by area of square, you will see the calculation pi r square by 4r square is equal to the area of circle by the area of square. R square gets cancelled, so pi is nothing but 4 times the area of circle by area of square. So far we have not done anything related with Monte Carlo simulation. It's purely the geometry which is telling me this, that pi is going to be 4 times this ratio, area of circle divided by area of square. Now I want to estimate the area of circle and area of square using Monte Carlo simulations. So which is basically the fundamental purpose of Monte Carlo simulation, that it tells you can use it to estimate the area of the given surfaces or area under the curves also. But here we are focusing on how to compute the area of circle by area of square. See, we are not interested in their individual magnitudes of area of circle and area of square. We're just interested in this ratio, right? So we do another diagram. So in this diagram you can see I have just considered this much portion of your total diagram. Because of the symmetry, you can see the area of circle by area of square, this ratio is same even if you take this much portion of your figure, because of the symmetry. So even in this portion, if you take this area of square and this 1/4 of a circle, or you can say half semicircle, and then also you compute the ratio, so this is going to be same because of the symmetry. So we have just made it 1/4, you can say that, of this much. So it's sufficient to do the calculation for this portion. Okay, so this portion has been highlighted here. So the area of circle means this area. So this is not looking like blue, but I have written this blue area by blue plus red. So this is blue plus red, because square, it has to be the complete square. So it's not just red area, it's blue plus red. So it's blue by blue plus red. So now my problem is just this much, only this much, you can say. So if I compute this blue area and if I compute this blue plus red area, so I'll be through. I'll be getting the value of pi. So now the question is how to do that. So using Monte Carlo simulation, we will generate a random point. You can say a dot. Let me just erase this a bit so we can understand it more clearly. Okay, so using random number generation, I'll be generating a point. So I have to generate 2 points this time, x comma y, because the point in two-dimensional plane has two coordinates. So I have to generate x as well as I have to generate y. So suppose the radius is 1, because you can take any radius because it's not playing any role. It's r square is getting cancelled, so whatever you take, so just fix it to 1 unit, right? So r is say 1 unit. And suppose this point is your 0, 0, the origin. Okay, so I'll generate these two random numbers x and y. So now I'll say that point falls here. So I want to count that as a part of the blue area. And then I generate another point, and suppose that point falls here. So that point I'll count in the red area, blue plus red area. So, and similarly this here, so blue area, this here means red area. So basically blue plus red is going to be the total number of points generated, because blue plus red, so howsoever number of points you generate will give you total number of points. So you only need to basically count the points lying in blue area, because in the denominator it's basically the number of trials, the number of points which you generate collectively. xy, means I'm calling this as one point, and to generate this as one point you need to basically generate two random numbers. So now what do you mean by point lying over here? So point lying in this blue area means what is that mathematical condition? Just like in the coin tossing example, the mathematical condition was that if the random number is less than 0.5, I count it as a head, otherwise I count it as a tail. So what is that mathematical condition which will tell me that how do I know that the point lying in blue area or the red area? So because it's a circle boundary and the radius is 1 unit, so this is obviously 1 unit. So if any point lying in the interior or even on the boundary of this, so it should satisfy x square plus y square less than equals to 1, because I have assumed this point is 0 comma 0. So the equation of this circle is x square plus y square equals to 1. So you want to count the interior of it. So x square plus y square less than equal to 1. And obviously we are generating the points non-negative lying between 0 and 1. Because obviously this is the first condition, the random numbers x and y individually cannot go beyond this, because your point cannot just lie out of the square, out of the total area. It has to be within this vicinity. So your y is also from 0 to 1, your x is also from 0 to 1. So individually you generate a point x and y between 0 and 1, and then you check this mathematical condition. If this is satisfied, you count it in the blue area, otherwise not. So you just do this 1000, 10,000 times. By this way you will have the number of points, the number of counts which you have got in the blue area. So this formula, will give you 4 times the number of dots in blue area, means basically the number of points satisfying this condition divided by the total number of points or the simulation runs. So that's how we have computed the value of pi. So this figure was just to show you that how this is working, but when you will be writing program for it, there you don't need to draw any circle or anything like that. Although we can have a visualization of it, but basically this is going to be like that. So that's a very interesting application of Monte Carlo simulation to compute value of pi while performing this experiment in the lab. So that's all about this lecture.